Hello, welcome to today's lesson. It is called Calculating Volumes of Solids of Revolutions. So you've been calculating volumes of lots of solids. You can figure out volume of prisms, of cylinders, of cones. Those are those nice shaped objects, but not everything is so nicely shaped. If you had to figure out the volume of, let's say, a pear, something is very different about that because it doesn't have this uniform length and there's no set formula. So we come around with a different means of being able to tackle any shape whatsoever. And it has to do with understanding graphs of functions and manipulating that graph on an x-axis or along a y-axis on a grid so that we have a visual manipulation of what that function looked like. So what does that mean? So I have put 3 videos on our Google Classroom because you really want to see, if I were standing in front of you right now with all my little props, I could show you the idea of something in motion and what we want to visualize happening. So these videos, definitely have a look at them, maybe even before listening to this lesson if you want to pause this and see what the idea is. So the idea is we have our x and y axis, and then we have some type of a function. Maybe it's a crazy function like this. So there's a portion of my function right now. So this is y equals f of x. So think of this as kind of a barbecue spit, all right? And we have the capability of taking this shape and revolving it and rotating it around the spit. Something easier to see, let's say, would just be a line. So if I had a line segment or a portion of a line, and I was able to take that and rotate it round and around in the air about this spit, what would it end up looking like? You would have this symmetry idea, and the motion that's being created is kind of outlining in the air a shape that will resemble a cylinder. And that's because this was a very nice uniform line. If I did the same thing here, and I took this shape and was able to rotate it, I would end up with something looking like that, and therefore filling in kind of this weird shape. I all of a sudden would have created something like that. And now I can use integration. That's kind of kinked there, all right? I could use integration to start figuring out what would the volume of this thing be, because now it does look like a solid, not just like a linear shape. What's happening then is when we talked about integration with area, and we had to figure out area of funny shapes, right? So we went from here to here, and we had our limits. We were able to figure out this area by slicing it. And we sliced it and sliced and sliced. And the smaller each slice was, the better my approximation for area would be. And really, taking such small intervals, so each one of these was called delta x, at a time, from going from one slice to the next, no, definitely this slice would not have the same area as a slice over here, but going through that very slow change from piece to piece, I got a very good estimation using this as a key factor, so using the function as a key factor. That's exactly what's going to be happening here. I'm going to slice this shape into all sorts of different pieces. And what would each piece look like? If they were small enough, each one of these pieces, if I could take it off to the side, it would start kind of looking, oh, this isn't good here, like a little disc. Okay, so every slice becomes just this disc, kind of like that. And some discs would be smaller and some discs would be larger. But that's what these start looking like, okay? So I'll have a better picture here if I just take my linear function and I say I've spun it. So now I've created really kind of a cylinder on its side. This right here, let's say was, if I stood the cylinder up instead, okay? So that line right there would have been this. So I've just taken this cylinder and tilted it sideways. So this value right here represents that right there. That is what we did this spin or this rotation around the x-axis. And when I took one of these slices, because I'm slicing, it looks like this. And the next step is I'm going to lay this flat. So I'm just going to push it over. So what am I actually looking at here? That's that little slice I'm looking at. What do I know about that? This function, this happens to be linear, it could have been curved, but that is f of x. that has a correspondence to the important parts of a cylinder. We call that the height, and we call that the radius, and we know those are the two components I need to figure out volume of a cylinder. So had this been sitting straight up, now the radius is here, right? That's your radius, and this distance right here, how wide it is, would have been the height. So this distance is my change in x values, so there's my delta x. And for that one piece right here, the radius, right? This radius is the distance from here to my function. How do I ever figure out that distance? It is just simply the value of the function at a certain x value. So that this radius is really going to be found from using the equation of the function that I was given. So same thing, no matter what this was, for me now figuring out the value of the function, I'm going to know the radius of this little disc. So this is called the disc method or a slicing method. So for me now to continue, what do I want? I want an accumulation or a sum of all these different slices. So if I want to sum up a volume of a big shape like this, and I know I'm dealing with pi r squared height, how can I substitute in different values right here? Well, pi is pi. What is the radius of this slice? It's f of x, but I'm going to be squaring that. And then I have this height, but the height was my delta x. So this is the volume for one disc or one slice, but I want to sum up, that's just this one right here. I want to sum up an infinite number of slices. So here comes our sum. So we could have gone back and used summation notation, but instead we represent this as an integral. So now I'm going to look at volume of this entire shape. So I would have my limits, you know, going from A to B. Then I am summing up all these little cylinders. So I have pi, I have this r squared, which was really my function squared, and we've seen before delta x is our differential dx. So now what else do we know? Pi is just a constant. So for the sake of easing up our integration, it's a good idea to move your constant out front. So now I have my formula for volume of any kind of shape. As long as I know what that top part of my graph looked like, I can find its volume by saying pi, integrating from A to B, from where this thing started to where it ended, of that function. And this is why on one of the videos you're going to watch, you just see all of a sudden magically this pi occurs out front of the formula that you're given. That's where it came from, because every single piece of the shape that you're trying to create, whether it's this one or this one, really resembles a disc. And we're looking, in other words, a cylinder, and to find volume of a cylinder, that's our formula. So that's where the pi came from. Okay, so there's the formula. So there's so many different shapes that you could get as you're looking at different functions. So if I had a line right here, picture that reflected, picture that line spinning, and now you would have that kind of shape. Now you would be able to, using the formula for this line, let's say it's negative x plus 5. Whatever it is, you would know I'm going to go from 2 to 6. I'm going to integrate. I'm going to picture this being cut into slices. I'm going to use this formula, and I can figure out the volume of something that previously maybe I didn't have a formula for. That would be a linear function. Let's say I'm given a radical function, right? So radical function, that went 2 to the right. Well, the idea, what would this look like if you could spin that piece from here to here? Well, now you'd have this. So think about the solid that would be created there. It's kind of a cup-shaped looking thing. How about if I had, let's see, a cubic graph, all right? And if I wanted to look at this part, and I'm going to integrate from here to here, there's now my solid. But slicing this into discs, every disc is really going to represent a cylinder. So the idea is we need a function, we need to know where I'm going to, that's how I'll integrate it, and then I'm going to rotate. So the idea is, for all these pictures I've shown you, we've rotated this way. You can rotate as well. I can give you a line over here, and I can say we're going to rotate it instead across around the y-axis. So now here's what shape I would have. Right? So if this spun this way, this line that I was given right here, I can still create these 3D solids. Okay? But the idea will always, and if I did that, okay, let's think about this one. Now I'm going from here to here. So in a previous video, I think I called this C and D. So now to get the volume of this kind of different shape, that pi will always come out front. I'm integrating from C to D, but now my function needs to be in with respect to y. This would all be squared, and the differential is dy. So I would just have to make sure I can isolate my x and put in my expression here using y's instead of usually we know we have x's here. Okay? Do remember that some of these shapes that we're going to end up with have formulas in math. So a minute ago when I took this one and I rotated it about the x-axis, I'm going to use integration to find the volume of the cylinder. But I also have a math formula that I could have maybe just used. Maybe I can check my work by just looking at the cylinder, finding the radius, finding the height, and doing a Math 10 approach and seeing what the volume is. Same thing if I took a line like this and rotated about the y-axis. Now I see I have a cone. Well, maybe why don't I just use a Math 10 formula for volume of a cone instead of using calculus? If that's smarter, why wouldn't you use it either to verify your work or get an answer more quickly? But these are those nice shapes that we've known. You're going to be dealing with a lot of not nice shapes, right? No one's going to call this a nice shape. But if someone gave me that formula, so this could be a trig graph, it could be a polynomial, I can always come up with the volume as long as I know the equation of the formula. So we'll do a couple. So the first one we will tackle here is, let's say your first example, you're supposed to find the volume of the region bounded by. So they're telling you kind of what's on top, how far you're going this way. So get used to that terminology. Bounded by x plus 2y equals 4. The x-axis and the y-axis. So are graphs helpful? You bet. You really should start by drawing yourself a graph. So I'm going to draw this thing. Maybe I want to put this into y equals mx plus b form. So as soon as I do that, I'm presuming I'm going to be rotating this way. Oh, and sorry, we are going to do this two ways. The first way I'm going to do it is, what shape would I get if this was rotated about the x-axis? So that's my kind of spinning axis. So if I were to isolate my y's here, I'm going to have this formula here. So I can now quickly draw this. I've got a y-intercept of 2. To find an x-intercept, I'd make y 0, so my x-intercept is 4. Okay, so this is, and it goes further. This is the line that I was given here. But where am I bounded by? It's bounded by the x-axis and the y-axis. So it's from here to here that they want us to make this thing spin. So if you made it spin, here's the shape that you now have, right? So it's really a cone if I turned it sideways and looked at it, but I'm going to integrate with respect to x. So volume will be, again, the pi will just sit out front because we are going pi r squared, but that now looks like pi function squared. So the pi came out. I'm integrating from 0 to 4. The function is negative 1/2 x plus 2. That is always squared dx. So now you can choose how you want to integrate this. Should I expand this or leave it alone? Well, you've got options. There's pros and cons either way. Expanding something really nice and easy first is probably a good idea. So if I were to expand this, I'll have negative 1/4 x squared minus 2x plus 4. So, and then dx. I think I'm right there. Okay, so now I'm going to integrate. So that pi would stay outside. Integrating here, I'll get negative 1/12 x cubed minus x squared plus 4x from 4 to 0. And working my way through, I'm just going to skip this. the details there, and that is my volume. If you are asked for units, right, it wouldn't be a bad idea to include the fact that this would be cubic units. Okay. How about if I didn't expand? Okay, so if I just kept it as is and instead used the chain rule, there's just something you need to watch for. Up here, if you're going to use the chain rule, or not chain rule, if you're going to undo the chain rule, you have to recognize that there's a K here that you're going to have to undo. So if you just want to leave this as is and integrate, you can. You will have your pi, but you're now going to have 1 over 3, negative 1/2 x plus 2. This becomes a 3. I'm using this formula, but I have to undo that k, so I would need that right there. This is my k. So I have 1 over whatever that value of k was. And then I'm integrating from 0 to 4. Working all this out, taking out any front constants, this would become a negative 2 on the top. So really in front, these two together makes this a negative 2/3. Probably haul it out, okay? So that negative 2/3 would stay with the pi. Now I have this negative 1/2 x plus 2 cubed, and I'm going to have to integrate now from 0 to 4. Is that less work? I don't think so. For the sake or the time it took to expand this, in this case that was easy to expand it, and then integrating was fine. But here now you will leave this out front, do all your integration, take everything through, you will get the same answer because it is the same shape. Then you could have said, I'm going to think back to good old Math 10, and how about if I just use the formula for volume of a cone and verify my work? So volume of a cone was pi r squared height divided by 3. So the radius of my cone is 2, the height of my cone is 4. I'll have pi 2 squared times 4 over 3. That's 4 times 4, so I'm going to have 16 pi over 3. So who needs calculus, right? I got the same answer that way, but it's a good check. So that was me rotating about the x-axis. How about if we rotated about the y-axis instead? Okay, so now this is going to be about the y-axis. The picture of the starting function would still be the same, right? From 2 to 4. But now we spun it this way. So there is now my cone. It is a cone, but it is not the same dimensions. The previous one had a height of 4. Our new cone has a height of 2. What are my limits of integration? I'm going from 0 to 2. So now volume would be going 0 to 2. But I need the formula in terms of y. So we were given originally x plus 2y equals 4. So that's easy to get the x by itself. It would be 4 minus 2y. So that's going in here, 4 minus 2y. Don't forget to square it, and then dy. So now you're faced with exactly the same choices. Should I expand, or should I be careful and notice there's a k of negative 2 I'll have to undo? And of course, could I just now find the volume of this cone using algebra? And geometry, sorry. If you want to try this one, the answer would be 32 pi over 3. So you have a choice. You can, but that graph or that picture, that sketch really helps you to see what you've got. Okay, one more, and that would do it, is if you were told, let's say, so this is our second example, to use integration to find the volume of a sphere with radius of 5. Okay, so a sphere with radius of 5. Remember, we want to picture this. So you want to see what, so of course the sphere, here's what we're talking about, and the radius is 5. That top graph, right? That's what we want to see, and then we're probably going to try and rotate it around the x-axis. So where do I want to draw this thing? I have choices. I could draw it here, saying I'm going to go from 0 to 10, right? That would give me a radius of 5. Or I could do this, say I'm going to go from negative 5 to positive 5. Either one of these, once I rotate them, I will have this sphere. So is it easier for me to find this formula, or is it easier for me to find this formula? Since we did trig and we dealt with the unit circle so often, we should remember the formula for any circle centered at the origin is x squared plus y squared equals r squared. That's any circle centered at the origin. So I'm going to tackle it this way. So my formula would be x squared plus y squared equals 5 squared. Isolate my y, so I have y squared equals 25 minus x squared. Square root both sides. So so this would be my positive root 25 minus x squared, and the bottom would be the negative. Well, I'm only looking for the top, right? We're going to take that top function. So that would be the formula that I want to integrate. Where am I going from? Negative 5 to positive 5. So to figure out volume, pi's out front, I'm going from negative 5 to positive 5. 25 minus x squared, but squared dx. So I could go and figure this out. Squaring will just remove this, right? So it's not looking too bad now. I'm going to integrate from negative 5 to 5, 25 minus x squared dx. That's a pretty nice integration. If I do that, I will get 500 over 3 pi cubic units. Cubic units. What else could I have done to ease up my work a little bit? Remember we talked about symmetry. The idea of symmetry, how about if I don't like this idea of, and we can see this was a symmetrical drawing, if I took half of it, if I said, you know what, I'm only going to take this, and this is what I'm going to rotate, I will end up with a hemisphere, right? A semi-sphere? Hemisphere? I would end up with this shape right here. And then I could double it. And that makes my integration so much nicer. Now I'm going to integrate from 0 to 5. So I'm not going to have to muck around once I do this, putting in negatives. It is so nice to put in a 0 into your integration work. So if you want to do this a little bit different and use symmetry, there would be a 2 in front of everything you're going to do. You still have your pi, but now you're going from 0 to 5. And what do you have? You still have the formula squared. So this, doing the integration for this, will be less work. Are you going to get the same answer? Yes, you're going to get the same answer. And last of all, if you can remember the formula for volume of a sphere from Math 10, you could have just done it that way. So volume of a sphere is 4/3 pi r cubed. That's geometry. So if I fill in my values there, I will have this. 5 cubed is 125 times 4 is 500 pi over 3 cubic units. So the math here isn't too tough. It's really nice to have your picture. Watch the wording in the textbook when they are trying to give you the boundaries. Make sure you're understanding whether you're supposed to be spinning around the x-axis or the y-axis. So the homework will be listed in Google Classroom. Like I say, do have a quick look at some of those videos so that you can just see what they're doing. They're trying to give you a look at starting with some function and breaking it down into, and then filling it in. And they do a really good job of filling that in and showing you in motion how the smaller the slices, the more accurate you get for a true blue estimate of volume of that solid. Okay, thanks for listening, and we'll see you next lesson.